Hello everyone, welcome back. So today we are going to first finish what is left in the last lecture on the CMOS scaling, and then we will talk about the SRAM starting from today's lecture. So this is where we have discussed. So the CMOS scaling, the technology node does not correlate with any physical dimensions on the transistor structure. As you see here, the gate length does not scale in the recent nodes. So what is really scaling is this CGP or CPP, contact gate pitch or contact poly pitch. So because the gate used to use the polysilicon as a material, so it's also called CPP. And also the metal one pitch. So here from the layout, you see that the contact gate poly pitch is the distance between the centers of two gates. And then the metal one pitch is the distance between two metal wires in the first level of the metal. So this will define the density of the transistor. And here in the future technology nodes, like 3 nanometer, 2 nanometer, 1 nanometer. So here this is like the projected gate pitch, contact gate pitch, and metal one pitch. So like in the 2 nanometer node, the contact gate pitch is about 42 nanometer, and the M1 pitch is about 21 nanometer. So this, of course, is a projection from the industry trend. And here we have another view of the contact gate pitch. You can also think it's the center of the contact wire for the source and the drain, because this is the same as this one. So because those transistors share the contact, as a source and drain contact between two adjacent transistors, so the CGP and CPP essentially are the same. So this is a typical transistor layout in the digital circuit today. And here we have some examples. For example, in the two input NAND gate, then we see the PMOS region, we have this kind of contact pitch transistor. All right, then if you use the CPP and M1 pitch to define the transistor density for different technology nodes, you will have those dimensions from Intel and TSMC. And as we discussed before, each company will have their own design rule. So you have to look at what is the real number to compare the density between different technology nodes. You cannot simply say 10 nanometer from company A is the same as 10 nanometer from company B. All right, so let's move on. So here we can also look at from the standard cell library point of view, because in the standard cell for the logic transistor, you have NMOS and PMOS. So typically you are going to organize that into the standard cell, for example, the standard like NAND gate or NOR gate or inverter. So if you do that, then this is like the cell for the standard logic library. Like this is like the cell height, and this is like the cell width. And in this cell, you have the NMOS region and the PMOS region. So here we show the FinFET technology nodes, like 14 nanometer down to future projected 3 nanometer and 2 nanometer. So here you see those the green ones. The green lines are the fins of the FinFET. And then the red ones are the gates. And then here the gray ones are the metal one pitch. And here the top and bottom are typically wider. This is for the power line, like your VDD and ground VSS. So this is for the power line, because you know PMOS you attach to the VDD, NMOS you attach to the ground. So here the standard cell height and width The height is defined as how many number of the metal one track is used. For example, here in the 14 nanometer node, probably you will have 9P, that means 9 metal one track, and 3 fin, that means for NMOS and PMOS. Each NMOS transistor will have 3 fins, those green ones. So have 3 fin for the NMOS and 3 fin for the PMOS. As you scale down the technology node, of course, those CPP, like here, those CPP, and then the fin pitch, so those are distance between those green fins, and then the number of track, and also metal one pitch. So this is like metal one pitch. Those will decrease for the technology node. But here I want to point out, not only the distance will shrink, but also the number of tracks and the number of fins will decrease with the scaling. For example, for 7 nanometer node, then here the number of tracks reduced to like 6.5, and then the number of fins reduced to 2 fins. So in the future node, then we're going to further decrease that number of metal track reduced to 5, and the number of fin reduced to 1. So you have a question? So in the middle, you may have a half track for the, so the design rule is, if you normalize that, is about half track, because in the middle, you may have a contact for the output. If you think about inverter, right, you have input and output. So then you have input contact, output contact, that's maybe in the middle, somewhere here. So if you think about inverter, right, so you will have inverter. So the ground VSS and the power supply VDD, those are top and bottom. And then the input, you may have some contact via somewhere here, and output, you may have some contact via here. So those may occupy half track. Okay, so here I want to point out the reason that you can do this so-called fin depopulation is because the FinFET technology, as you scale down, the fin height will increase. So if you think about the FinFET, we'll talk about that in more details later. And if you think about the fin, so the fin height is going to increase with scaling. So that means one fin, you can deliver more current. So if the fin height increase, then one fin can deliver more current. So in other words, in the older technology node, maybe you need to use 3 fin to deliver, for example, 100 microamp current. But in the newer technology nodes, you may only need 2 fins to deliver the same amount of current, for example, 100 microamp. This is because each fin is higher in the newer technology node. So you can deliver more current per fin. Therefore, you can use less number of fins to deliver the same amount of current. So if you make the fin higher and higher, then you can use less number of fins to deliver the same amount of current. That means similar circuit speed. So you can save the number of fins. That means you can reduce the number of tracks here. So the scaling is assisted by the depopulation of the fin or reduction of the metal track. So this is another way to increase the integration density, even though we know that the gate length does not scale, and also we have difficulties further scale CPP, scale the M1 pitch, but you can further do the third dimension, because you can make the third dimension higher and higher, then you can further increase the density from this perspective. And in the future node, so here, like 3 nanometer or 2 nanometer, that's one possible way to further reduce the number of metal track. That is to get rid of the power supply, like your VDD and VSS. So the idea is to bury the power line underneath the silicon substrate. So you don't put the metal lamps on the top. So here, if you think about the cross-sectional view of the transistor, so what you can do is, for example, NMOS and PMOS. For example, previously, normally you have, let's say, if this is a VDD power supply, you have it here, so you need to occupy like a metal one track. In the future, so there's a proposal to make this power line on the back side of the wafer. So you have the metal line somewhere here underneath. You can make it somewhere underneath here and make a contact here. Therefore, you can save the space for the metal, for the power lamps. So those are the future trends, not in the production yet. So any questions here? Getting ratio. So here this is normalized. 40 nanometer if you think is 1 in the like total area for this library. So this is a relative scaling. All right, so then let's move on. So far we talked about the logic transistor. So here this is applied to the logic transistor. Those scaling will not apply to the memory. Here, when we talk about the memory, we mean the standalone memory. For example, the DRAM and NAND flash. Of course, SRAM is on the same chip with the logic transistor. So the SRAM probably will follow similar design rule as the logic transistor. Not exactly the same. Roughly, you can think the logic transistor and SRAM transistor are kind of same transistor. But for the standalone memory, like DRAM and NAND flash, so the definition of the pitch is a little bit different. For the DRAM, so this is defined as a metal one half pitch. F is defined as metal one half pitch. For example, if you think those two lines are bit line 1 and bit line 2, so the half pitch of those bit line distance will be the F for the DRAM. So the DRAM's feature size is more relevant to the DRAM's so-called technology load. So in other words, the memory companies are more honest in the technology node naming. That means the memory, if it's 20 nanometer DRAM, that means really the metal one half pitch is 20 nanometer. And then similarly for the NAND flash, so for the NAND, we will learn that more details later, but it's basically a series of the floating gate transistor between two contacts. So those are the floating gate transistors. So if you think it's 2D transistor, then you will have those 2D transistors in series like this. Then the poly pitch, because 2D NAND typically use like polysilicon as a gate material. So this is poly pitch. So this is defined as 2F, and half pitch is defined as F. So here one feature of the 2D NAND is that between those transistors, there's no source and drain contact. So if you think this is source and drain, and between those two poly pitch, there's no contact. Here, no contact. This is a way to improve the density of the NAND flash. This is a key difference. Because in the logic transistor, typically you will have the contact between two poly gates. But in the NAND flash, you don't have the contact in between. And then if you think about the 3D NAND flash, then the pinner pitch, because now you have two pinners, you basically tilt the NAND string from horizontal to vertical. So if you do that, then you have two like a cylinder or pinner. Then the center of the pinner, this is like the pinner pitch. So this is about 2F. So this is 2F. This is 2F. top pitch is defined as F. And in the 2D NAND and the DRAM, the F is essentially the same as the technology node. As I said, memory companies are honest in the naming. If it's a 20 nanometer, that means really F is 20 nanometer. But 3D NAND is a different story. We'll talk about that later. Because 3D NAND, what matters is number of layers instead of distance between two pillars. So we'll discuss that later for the 3D NAND. So any questions here? All right, then let's move back. For the logic transistor, so here we just show some key technology innovations for the scaling. In the 90 nanometer node, the string silicon was introduced to the channel to improve the mobility, the N-type channel and P-type channel. For the PMOS, the uniaxial compressed strain from the source and drain is changed to silicon germanium, and then this can basically apply the stress from the source and drain to basically squeeze channels horizontally. Then the band structure of the silicon in the channel will change. Therefore, the mobility of the holes can improve. And also for the NMOS, there will be like a silicon nitride capping layer on top that will introduce so-called tensile strain. That means we are going to push away channel. You are going to stress out channel. This can improve the electron mobility. So here, the strain silicon was used in 90 nanometer and all the way down to today's transistor. All the generations use the strain engineering. And then in 45 nanometer, high-K metal gate was introduced. This is to replace the polysilicon gate and silicon dioxide with a metal gate and high-K material. High-K means higher permittivity or higher K constant, dielectric constant. Typically, high-K material is based on hafnium oxide. But of course, the exact composition, companies may not disclose the exact composition. But typically, it's hafnium oxide-based high-K material. That means this interface will be like hafnium oxide. And then this will help with the gate leakage. Because as we scale down, there might be the turning current through the gate. Use high-K material to cut off the gate leakage. And then a 22 nanometer FinFET was introduced. So this is, as we discussed, a non-planar transistor. This is to make the channel, let's say make a gate surrounding the channel with the three surfaces from the top and two sides. This basically increases the coupling from the gate to the channel. Therefore, this can improve the short channel effect. Because gate now has better control of the channel because of the overlap of three sides of the channel. And then in the future, okay, next 3 nanometer, it was projected that this kind of stack nanosheet will be used. This is not in production yet, but according to the sources from industry, like TSMC, Samsung, they may all switch to stack nanosheet from the 3 nanometer technology node. So this is basically a gate all-around structure. So here that means the gate will surround the channel, four sides. So it's a gate all-around called GAA, gate all-around. And you can stack multiple sheets vertically. This is a way to increase the current density without using natural space. This is a way to improve the density, as we discussed. Because we run out of space in the natural dimensions. So the future is always the third dimension. You have to go vertically to increase the transistor's density. And here there's a video made by Samsung. You can look at this if you are interested. This basically outlines the technology innovations and the future directions, highlighting this kind of stack nanosheet transistor from this video. I will not play today. You can look at that after class. And then the question is what possibly comes from after the stack nanosheet. So let's say if 3 nanometer is nanosheet, then what will be the future after the stack nanosheet? So here I just quote one paper from Intel last year presented at IEDM. So this is of course a research paper, but this might be the future direction to go for the industry. So the idea is to make the monolithic 3D like NMOS on top of PMOS. So here you see the evolution of the technology. In the old technology node, you may have the planar transistor, and then PMOS and NMOS like this. Using this inverter, then you have PMOS and NMOS region. So okay, basically here you have the gate, and then this is a channel. Sorry, actually the channel is in and out of the plane, so I cannot draw it like this. Channel direction is in and out of the plane. And then the first innovation was this FinFET, as we discussed before. And then the nano ribbon, Intel call it nano ribbon, but other companies call nano sheet. So basically it's still like a film, but you cut those fins into small like sheets or ribbons. So basically this can increase the gate to the channel coupling, as we discussed. So here the gate only coupled to the channel by 3 sides. But if you cut it into small ribbons or small sheets, then the gate will cover the channel all around. And this is possibly, as we discussed, introduced in 3 nanometer node. And after that, then the possible direction is to stack the NMOS on top of PMOS. So here you see previously we have, even for today, the NMOS and PMOS are separate on the silicon. You have NMOS region and PMOS region. But in the future, probably we can do this, right? Make the NMOS region all the way up, and then you can stack NMOS and PMOS vertically. So this is to make an inverter like vertically. And from the layout point of view, basically you can half the layout. So this is the layout. You used to have the NMOS here. This is NMOS, and this is PMOS. Now you stack, so then N and P will overlap vertically, so you reduce the area by half. So this is a way to further increase the density. So there's still many possibilities for the future. At least I see the industry has a roadmap for the next 10 years. Of course, after 10 years, we don't know what will happen. But at least there's a roadmap for 10 years, till 2030. Question? Where is what? Body? So here you can think it's like SOI, there's no body contact because nano sheet, it's already like all around. So there's no body contact. It's more like SOI. All right, so this is a future trend. We will see. This is not in production yet. All right, any questions? Yes? All right. I don't hear you clearly. Circuit splicing. Splicing, what do you mean splicing? Splicing, you mean? Yes. You can cut, you mean? No, it's a stacked vertically, so it's a sequential fabrication process. It's not stacking. So you fabricate the bottom like NMOS region like this, and then you grow those materials layer by layer. So it's not stacking. It's not you have 2 N and P and then you stack. No. Light blue. Or Oh, you mean here?
Yeah, what are those?
Oh, those are so-called STI. It's a shallow junction like isolation. Shallow trench isolation, actually. Shallow trench isolation is oxide. So it's to separate different regions. Like NMOS and PMOS, you used to use STI to separate the N and P. So here, as I said, this is in and out of the plane. So you think the source and drain is something like this. It's not horizontal. It's in and out of the plane in this schematic. All right, let me see if there's any questions from the online. So first question, for the 2 nanometer load, we don't use NMOS part anymore? No, as we discussed, this is a stacked probably. So we will have NMOS for all the technology loads. Second question is, how are the nano ribbon connected to each other? Are there wires somewhere that connect them all? Yes, this is a very good question. Yes. So in this schematic, we don't show that. But as we discussed, in and out of the plane, you will have the contact. In and out of the plane, you will have the contact like maybe vertically somewhere, something like this. Or in the top view layout, you can think this is like the contact. Sorry, this is like there's like two pillars standing up, so you can collect all the sheet to those contacts. Yes. Or you can think here this way. Oh, this is another cartoon, right? So you see here there are like nano sheets. They will be at the source and drain region. Then they will be connected together. So actually, this 3D view shows better connections in those. And you have sheet here connected. Because NMOS and PMOS, you know, the NMOS and PMOS from the circuit point of view for the inverter. So this is a way out node. So the NMOS and PMOS drain contact. This is the drain, let's say, drain contact will collect it together. Yellow like pillar going to collect the way out for the NMOS and PMOS regions. All right, so let's move on. So finally, in this lecture 2, I will spend a few minutes on the industry landscape. So this is not technical, but just for your information. So the total memory market. So this is the statistics from last year. The total semiconductor revenue is about 466 billion. This includes everything. But if you break down that into the memory, so here's memory really means a standalone memory. Standalone memory. That means DRAM and NAND flash, or maybe some no flash. So here we have some others. Basically, the memory, standalone memory, occupy like 27%. That's about 126 billion. And within this 126 billion, so roughly half and half DRAM and NAND flash. So you see how big the market is. And here, those are the semiconductor industry models. So first of all, we have the foundries. Those are manufacturers. So foundries will not do the design of the circuit, but you will just do the fabrication. So of course, you know TSMC is the largest foundry in the world. And then there are others like Global Foundry, UMC, SMIC, and so on. But of course, TSMC is the leading one with more than 50% of the market share. I believe 55, even close to 60% these days. The foundry business. And TSMC has the latest technology among all the manufacturers. And then fabless, that means design house. So those companies only do the circuit design, the chip design, and they will send the designs to the foundries for fabrication. So of course, the interface will be the GDS, the layout files. So if you are a circuit designer hired by those fabless companies, your final product or final output from you will be the layout GDS files. And here we see like Qualcomm, Broadcom, AMD, NVIDIA, MediaTek. This is a long list. Go through that. And then the third category is called IDM, Integrated Device Manufacturer. So this one basically does both foundry and design business together. So it does everything. So those are giants like Intel, Samsung, they do everything from the architecture design down to the manufacturing. But Samsung also offers the foundry services to others. Samsung also has a separate department for the foundry business. And then the recent news, as you may have seen that on the social media, Intel, after they changed the CEO earlier this year, they decided to do this so-called IDM 2.0 model. That means it will do the IDM by itself, but also it will collaborate with others. For example, Intel will send the design to TSMC for fabrication for their future processors. This is because of the delay of Intel's process. Okay? And also Intel will offer their manufacturing to others. So Intel will also provide foundry services. And I just saw the news like the DoD, Department of Defense, signed a contract with Intel. So Intel design the chips for DoD applications. And then the last category is memory companies. So those are the standalone memory companies. They are like a little bit different. So they are more like IDM because those are basic design and fabrication are together. Like Samsung, of course, a big player in the memory business, and also SK Hynix. And there is a news that SK Hynix will buy the Intel's memory business. So Intel used to have their NAND flash business, but then according to the news, Intel is going to sell that SK Hynix by 2025. And then Micron is a big one in both DRAM and NAND flash. And then Western Digital used to make the hard drive, but a few years ago, Western Digital acquired SanDisk, and now Western Digital has a big business in the NAND flash, but it does not have the DRAM. And then Toshiba, and actually is the inventor of the NAND flash, and Toshiba, not in a good shape a few years ago. So Toshiba's memory spin off company called Kioxia. And then the news just a few days ago, I saw that Western Digital is discussing with Kioxia, so probably Western Digital will buy the Kioxia in the future. It's not finalized yet, but basically you see the industry consolidation is happening. So there are fewer and fewer players in the field, especially for those advanced technology nodes, also the memory business. All right, here are some historical trends in the revenue for the top semiconductor sales. So this was back in 2006. And at that time, you see that Intel #1, Samsung #2, TI, Texas Instruments #3, ST is ST Microelectronics, is a foundry in Europe, and then Toshiba, and then TSMC. So this was like 15 years ago. So this is the ranking at that time. And then let's see how the ranking changes over the years. And then now we are like 2010. So you see Intel number 1, Samsung number 2, Toshiba number 3, but mostly is a memory business. And then TSMC is ramping up, number 4, and then TI drops to number 5. But for the first time, you see Qualcomm popped in the top 10. So this is the rise of the mobile phone business. And then 4 years later, you see the ranking changes. Intel number 1, Samsung number 2, now TSMC become number 3, and then Qualcomm become number 4. This, because of your smartphone business. And then at that year, Micron acquired Epida. Epida is a company in Japan making like those DRAM. And Micron acquired Epida, now become number 5. And then we also see SK Hynix, the South Korean memory company who does both NAND flash and DRAM, ramp up. So this is 2014. And then 2016, roughly the same, like Intel, Samsung, TSMC, Qualcomm, and so on. And 2018, now you will see that the memory business really kick off. So Samsung become number 1 because Samsung is dominate in the memory market. And then Intel dropped to number 2, and SK Hynix, a pure memory company, ramped to number 3, ramp up to number 3. And the Micron, memory company, DRAM and NAND flash. So this is the era for the memory. Because nowadays, the most important part for the computer system is about memory. Of course, the computing is important, but nowadays, memory dominates the market. And then this is just last year. Again, like those 3 memory companies are in the top 5. So any questions? All right, let's have a quick summary. So basically, we talk about that the technology node, and nowadays it's more like a symbol for the logic transistor. And this is defined by different companies. They may have different design and naming strategy. And then the contact gate pitch, CGP or CPP, and M1 pitch determines the density of the logic transistor. And also, we see the standard cell height can be reduced in the FinFET technology nodes because we can make the fin higher and higher. And in the future, for the stack nano sheet, we can make the number of sheets more and more. So you go vertically, and then you can make the lateral space in the standard cell smaller and smaller. And then the technology node name for the DRAM NAND flash is more related to the smallest spatial size in the physical dimension. And then we see the technology path from FinFET to stack nanosheet to the monolithic 3D NMOS on top of PMOS. And the last point is that the memory market is an important piece of the semiconductor. And you see 3 out of 5 top 5 vendors are memory companies. All right, any questions? Okay, let's see if there's any questions online. No, then I will break this